And one of the things that I discussed during the presentation was the changing in the fire ground. In other words, what is it different that the fire service people are seeing than they were some years ago? But more importantly, in terms of the training, they probably were trained on the fire situations that were much older than what they are seeing right now. And we feel that's one of the reasons why we are seeing a larger number of fatalities per number of fires that they respond to. And so we'll cover upon several areas that deal with changes in home severity, or really changes in how our homes are being built, and what impact does it have. And I have several different concepts that I'd like to share with you. Two of the problems I'll be looking at are directly related to firefighters themselves. Second one is more related to how the alarm systems, smoke alarm systems in our homes work. Because that also has impact upon firefighters having the need to go into a home for search and rescue, which is times when they are most vulnerable from injuries and exposure to high gases and temperature. So I'll first go over a little bit of the US residential fire statistics. Then we'll look at how things have changed in our contemporary homes, the homes we live in right now. My focus is still on the US. I'm still trying to learn about how homes are being built in Netherlands, and its applicability of the research from there to here. And then we'll talk about some of the UL research related to these new challenges. What I'd like to do is, because today is a masterclass, feel free to ask questions anytime, because I would like to make it interactive. Maybe your feedback during the presentation may remind me of something that may be important for discussion during this presentation. So while I have the material, I would say it's not cast in concrete. We can certainly have discussions around the topics that I'm knowledgeable in. So we talked about a little bit earlier about reduction number of fires. Way back in 1970s, which is when this first started collecting the data, we had a fairly large fire burden in the US. And I think around that time, we had about 13,000 fire deaths in the 1970s. Now, this time is very important because in 1975, something very important happened in the US. The US Congressional Committee developed a small task force to look into the US fire problem. And they created a very important document called America Burning. So if you really want to look into how the science of fire has evolved in the US, it really starts from 1975. Okay. Now, that doesn't mean that we did not know about fire science before, but there was not that much of emphasis on investigating the science of fire dynamics until that time. And so if you look it up on Google, you'll find the report very readily. It's a really interesting report. But one of the things that it required the US government to do was to start collecting and analyzing fire incident data. So they started collecting data, I think, 1976. And the first year they had the compiled data was in 1977. And since then, we've been having progression of analysis of data. So we know in fair amount of detail where fire occurs, who does it impact, what are the various causes of fire, et cetera, in fair amount of detail. We also know, by the way, whether sprinklers work or not for the statistics. So we found that, for example, sprinklers in homes do save lives and do reduce property losses. Smoke alarms have found to be very important in that area also. You can look in the fire statistics and show the impact of smoke alarms since they were introduced somewhere in the mid-70s. So these statistics are really important. We had a fair amount of decrease in number of fires, but again, 272,000 one and two family structure fires is still a pretty large number. Here's another interesting statistic. I saw it recently and I had never connected, but I just kind of realized that this is very strange. While the number of fires have decreased, number of deaths per fire, it's not really decreased as much. So obviously something is happening in our homes that is not allowing us to get the full benefit of the reduction in number of fires. So to me, it seems that the fires are getting more severe. We're getting less number of fires, but they are more severe.
How does the American figures relate to other figures around the world?
So, as I mentioned, the US statistics have shown that we have much higher burden, and European countries are doing much better than we are in this area. I can't remember the statistics for Netherlands, but I believe they're about half of what we have in the US. And some other countries are even better. Per capita, yeah, exactly, per capita. This is all per population or number of fires per population. Now, one thing I have noticed, though, in some countries, this curve is starting to go up a little bit, especially in Sweden. I looked at the data for Sweden recently, about 6 months ago. I was surprised that the number of fires are going up in Sweden. I'm not sure what's happening in Netherlands. Then I asked Ricardo to see if I can get some statistics, get a good understanding of fire events in Netherlands and maybe in the nearby countries. It's a good question. So what is happening? Well, several things have happened in the last 15 years. This is relatively new for building construction industry. It's not the iPhone in our timeline, but in our timeline, it's considered to be pretty quick. In the US anyway, we are seeing much larger homes, more open spaces. So when you build larger homes, you try to create more open spaces. So you have the image of grandeur, for example. The type of materials we have in the home is also changing rapidly. And again, the construction techniques are such that we have much more open spaces so that if fire were to start, for example, in this structure, it can actually travel unimpeded by natural barriers you might have in your more smaller contained rooms from one end to another end, because you have all these open spaces. And finally, we talked about changing in our construction method. We are going to lighter engineered products that are actually better in so many ways. It actually uses less wood, for example, for the same strength properties. In fact, they are lighter so that your transport load is less. So therefore, you're consuming less fuel transporting this pre-manufactured items into a job site. And that also saves fuel, and that's a great benefit. So we don't want to change any of this, but we want to understand what it is. And we want to understand the impact of these changes to the fire service. So typically, we notice faster fire propagation and shorter time to flash over, rapid change in fire dynamics, shorter time to collapses, and these last two times have some big impact upon the fire service. An idea of the fire statistics, of size statistics. In 1970s, typical homes were small, single ranch, we call a ranch style, single-story homes. But they were about 1,500 to 1,600 square feet. I remember when I first joined UL, one of my projects was to do risk assessment of homes in the US. And this was back in 1980s, and we were looking at home sizes about this size, about 1,500 square feet. Today, you'll find homes are more like mansions. Even for me, this is a big home, but this is kind of turning out to be fairly common in the US, in many parts of the US, to build big homes. Smaller lot size, but big homes on the same plot size that you might have. Getting to be more than 3,000 square foot now on an average, which is a pretty significant change. Now, how does that change things? Well, for one thing, you have more air available than you had before. So even when you have a fire, the fire doesn't become ventilation controlled that readily, but it can grow. It can become much bigger before it becomes ventilation controlled. So that's a change in fire dynamic that comes out of having a larger home. Some typical floor plans. I show that only because I wanted to show there's this concept of a great room in the US these days, where as you enter the home, you have a very tall atrium space. Your ceiling is about 17, 18 feet high. Okay, when you get in, you feel, wow, you come into a Hollywood mansion, right? And that's the impact that I think the builders are trying to give the building owner. And then also the rooms are relatively larger because the overall floor plan is bigger. Some examples of photographs of what we're talking about: great rooms, high atrium spaces, open foyers, 14-foot ceilings. I've seen it's very common, 12-foot, 14-foot ceilings. My home is built on 8-foot ceiling because it's a 1984 home. If I were to get a home manufactured for me now, it'll be about 12, with typical sizes, 12-foot ceilings, okay? Because that's what the builders have built for you. And it looks good, so that's why that's how you build it. And big floor plans, big floor plans. But one of the biggest changes in the last 20 years is the materials we use. And I kind of use a clip. How many are old enough to have seen this movie called The Graduate? Or have seen the movie Graduate? Okay. So you'll remember this scene. It's very important for us because its consequences are amazing.
What are you going to do now?
I was going to go upstairs for a minute.
Oh, I meant with your future, your life.
Well, that's a little hard to say.
Ben.
Excuse me. Mr. McGuire.
Ben.
Mr. McGuire.
Come with me for a minute. I want to talk to you. Excuse us, Joanne.
Of course.
Thank you.
It's just I look at him and I can't believe it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
Plastics. I wish I had connected the dots in 1968 when I saw the movie. Because then I would have understood what's going to happen. That's what we have in our homes these days. In fact, we have a friend, a fire service friend in near Northbrook, and he calculated, I don't know how he did it, but he calculated typically would have about 1,500 pounds or 100 kilograms of plastics in your home. Think about sofas and carpeting and clothing and everything you have. Everything has got synthetic materials in it these days. Shoes, toys. You can't buy wooden toys anymore in the US. It's hard. You have to actually special order wooden toys in the US. They're all made out of plastics. So this is a graphic from National Geographic magazine, which is very nice for us because it shows what we're dealing with at home. And this is all we would consider as a fuel load. In case there was a fire, what's going to burn is actually this. The structure gets into the picture much later into the fire game. And then in addition to that, you have this pretty large spaces where you're going to put all your plastics in, all your furnishings in. You have fairly good open spaces. In fact, the construction practices have changed. We used to have horizontal barriers in the home. Well, no more these days. In fact, there are spaces available for your fire paths to go from bottom, if a fire to occur here, to the upper floors. And then what is happening is changes in our other construction. The sheathing materials are changing, outer materials are changing. For many reasons. One of them, obviously, is energy efficiency. As you want to make homes more energy efficient, you are going to use insulating materials on the outside so you get more thermal insulation and keep the heat inside, or the cold inside, depending upon the type of the time of the year you have. And we are doing some research in that area to understand how sheathing materials may impact fire growth, especially exterior fire growth. And these are the series of experiments. I think they're linked to the attic fire project that we are starting to work on right now. Because these fires from the outside would then end up into your attic space. The attic space fire is probably, I don't know how many firemen you have here, but it's one of the harder fires to fight because you've got to go on the top of the roof, cut an opening, and make yourself pretty vulnerable in that situation, and then you put water in the attic space. So it's a tough fire to fight, and we are seeing that now. More insulation in the attic space. Again, this insulation, even though there may be fiberglass, what binds the fiberglass? Right? You have a resin material that binds the fiberglass, and that's just more fuel. And that's what you're seeing right now. This is a photograph of a fire that occurred about 8 months ago near Chicago. Okay. Not exactly sure how the fire started around the garage area, but you can see that it's become from exterior, it's become an interior fire. We used to have fires that start from the interior, become an exterior fire, and we call it structural fires. Now we're seeing the opposite. We're seeing exterior fires becoming interior fires. And those fires are dangerous for fire service people. And then we are saying that since the homes are, bigger homes are built on smaller lots, the spacing between the homes have reduced naturally. You've got to put the big home someplace if the lot is smaller. And we are seeing fires starting from one building to another building. You can see, I mean, this is now happening. I wouldn't say these are frequent events, but these are events that we did not have before. In 1871, Chicago had a very bad fire. Everybody remembers the big fire of Chicago in 1871. Okay? That destroyed the city. That was a fire, that wind-fed fire that went from building to building and destroyed most of the city of Chicago. Okay? We are seeing those kind of fires occur now in our suburbs, not in the city, but in the suburbs, okay, because of the way we construct our homes. So we have many projects that we're working on that actually hit on the increased severity of fires. I covered some of them in the morning, so I felt maybe I should do something different for the afternoon session because you were all there for the morning session. So I picked a few projects for us to discuss as examples of the research that's going on to develop data, create a base of knowledge that the fire service can use. What I've done is that the projects on this side are all related to firefighter safety funded by Department of Homeland Security. But because we know this is a very important issue for UL as a safety organization, there are many UL standards involved in products that go in your home to make it safe. One of them is your smoke alarm project. Smoke alarms that go in your home are UL listed. And we wanted to make sure that the smoke alarms that are listed by UL are relevant to today's fires. So we did a research project to understand how the smoke characteristics have changed that might maybe make the smoke alarms not as responsive as we would like them to be. So that is a project that I also am going to discuss today as part of my discussion. Many of you may have seen these videos and the test that we had conducted. We call it the modern room or contemporary room, where you have plastic materials, couches and carpeting and curtains, etc. And then we have what we call legacy room, where you use mostly natural materials. Very hard to find, by the way. To find a couch like this that's made out of cotton, for example, it's not easy to find. Okay, you have to go to some antique stores, and then you have to make sure that indeed they're selling you the stuff you want to use in a fire test. But once we do this, we actually acquire a number of pieces at the same time. So we have similar samples when you want to do identical type of testing. And what you find when you do this testing in the different room sizes, that when you use natural materials, you get flashover time in about 30 minutes. Okay, this is what typically firemen in the US were trained to understand. You got 30 minutes to go out there and put a fire in 30 minutes before you get flashover. Well, with modern furniture, the time is really reduced to about 4 minutes. Right. So by the time the fire service is able to respond to your home, it is in many cases when you have content fires such as furnishings, you have reached flashover conditions. So they're actually addressing your fire at a point where it has become very dangerous. It's now going to be progressing into structural fires. They will think about protecting houses next to the building that the fire is in, et cetera, et cetera. They have to protect the people around, evacuate people around it. And so it's a much difficult problem than they had before. This video has been sped up so that I don't want to spend 30 minutes watching it. So it's, I think, by about a factor of 6. So you see people walking really fast. They're actually not really walking very fast. It just appears to be so. But you can see the fire growth with natural is much faster. You get a bigger, faster plume. You get a very thick layer, smoke layer, which is nice to see. Smoke starting to pour out from the structure. whereas in 4 minutes, the fire in this other structure is still growing. It's not run out of oxygen yet. And in close to 5 minutes, this is now ventilation controlled. And you see that, oops, there is no more smoke coming out because it is not very actively burning. It's just smoldering inside the room. You can see small smoke about still leaking out. And this will continue for another 20 plus minutes. So I can speed this up a little bit. But you get the idea, if I can see it. Okay, let me go back a little bit. Right. At some point in this other structure, they open up a window to get ventilation in. And sure enough, a little bit afterwards, you get flashover, right? Which is what Professor Bjorn talked about in the morning. And by the time it became ventilation limited at 5 minutes, and when after we opened it in about 2.5 minutes, we had flashover. So when a fire service person goes out there, he's trying to do his thing. He sees there's no smoke coming out. I'm going to open up a window to see if there's anybody inside. And as they are entering the building structure, flashover occurs, and this is where they get hurt. This is going to speed up a little bit more, and it's going to become ventilation limited. I think in about 20 plus minutes. That's the nice thing about speeding it up. You can, you don't have to wait for full 25, 30 minutes to watch the video. Okay, now it's slowly, you can see that it's starting to consume the oxygen. There's still a lot of fuel left, by the way. Okay, it's just there's not enough oxygen, and they're getting ready to ventilate. There you go. And the so to speak, the clock starts again, and you can see the fresh oxygen inside this ventilation path provides the oxygen required to reignite the materials. This is a 1,600 square foot structure. Okay, that's your flashover. When you get the flames coming out, that's the indication of flashover. So it took about 8 minutes after ventilation, even though there was unburnt combustion products in that room, partly because the type of fuel you had is slower burning natural materials. Okay, so what does the data show us? I think this is in my mind, an interesting part of understanding what we saw quantitatively. So if I look at the red line is the ceiling temperature in your oldie type furniture, old furniture, cotton-based materials. About 20 minutes, you had ventilation limited. You saw the fire come down. The temperature also comes down, very much like the curve that Professor Bjorn Carlson showed in the morning. And then you open the ventilation, and then you get reignition, and then you get flashover. But that takes about 30 minutes to get to flashover. In this case, you get ventilation limited condition in about 5 minutes. You let it sit for a few minutes. You open the ventilation, and very quickly it comes to flashover. Okay.
What is the first after the ventilation? What's the first peak? The temperature rises and then drops again before flashover.
This one here?
On the red line.
On the red line.
Oh, this one here.
Yeah.
Yeah. Okay. It's still burning. Mm-hmm. Yeah, it's still growing slowly. The fire.
Why does the temperature decrease?
Why is the Oh, I see. I think it's just balancing out the oxygen. It's just getting more oxygen. You'll see it in the video if you look at it. The hot gas layer at the window is starting to drop. Mm-hmm. Okay, so you're getting less oxygen, and then at some point you get sufficient energy back into it again, so you get flashover. Good question. But another thing I wanted to point out is the oxygen concentration in the room. Okay, in the modern room, you'll see that when it comes to about 14%, 13 to 14% oxygen concentration is when you have indication of ventilation limited condition. Okay, that's a point where there's not enough oxygen to support combustion. This is fairly well known, is that if you want to put out a fire, you reduce the oxygen concentration about 15%, you can actually kill the fire, but just by reducing oxygen concentration, okay? You'll see the same thing happen in the modern, in the legacy furniture. So if you look at the data here, it's about, you get ventilation, it's about 18%, I take that back, but about 18% you see that there is very little, the combustion ceases out here. And that probably may be related to the materials being used in this particular product, the cotton-based materials, okay? The difference between two conditions, between the two tests is this time to flashover, which is almost about 20 minutes, 20-minute difference. So if you can get 20 minutes back into the structure, that could actually protect the fire service significantly. The problem is that when we started adopting photovoltaic panels, the fire service was the first one to say, you know, we don't understand the hazard you're asking us to address when you come to these events. So in many cases, they had, in the initial cases, they actually would come to the event and they had to struggle to figure out how to attack that particular fire because the photovoltaics is energized, there's power running to it. There's several challenges to it. This is from a fire service fire chief in California.
Well, we weren't sure what we had. We knew that...
This is on a commercial installation on top of a roof on a, I think it's a Target store in California.
So we didn't really know what to expect, so it was kind of an unknown when we got here.
And that's typically what the response was. We really don't know what to expect. And the reason for that is there have been many fires involving photovoltaic panels. Some of them have been pretty large on larger facilities. Some have been on residential homes. But in most cases, these fires start very early into the installation. So what does that suggest? There's some problem in the installation, all right? And you'll see, I'll show you some photographs to show why that would be the case. Now, obviously, many of these problems are correcting, so these are not recurring problems. But we had some pretty big fires. Actually, there's one in Bürstadt, Germany, a 5 megawatt service on a commercial facility. In that particular case, the fire service came to their installation, and they stopped, did not do anything, only because I believe it had to do with some union rules. They were not trained to fight that fire. Okay, and so the 5 megawatt facility burned down to the ground. And there have been several other instances of pretty large fires. In this particular case, the installation was such that there was partial shading of the photovoltaic panels. One of those more dangerous things to do when you install photovoltaic panel. You want to make sure that it is not in partial shade. When you have partial shade, there is localized heating that occurs in the junctions of the electronics. And that causes overheating and ignition. It's happened several times, so people now know this, not to do this. But if you have a home, you built it, did not know this, you installed, you know, you want fire service to come and protect your facility. This is a system in Italy, a 1,000 kilowatt facility. This also was actually not installed properly in our view because the angles of the panel was such that at a certain point of the sun, the lower panels were partially shaded by the panels in front. And that caused a very large fire. It destroyed a significant portion of that facility and the roof system. This is the Bakersfield. You saw the fire chiefs talk about it. He was talking about this facility. It's on a commercial installation, a fairly large installation, but it had to do with installation again. This particular power cable in a conduit was not aligned properly, and it caused localized arcing, and we had destruction of a few panels in this case. This is in North Carolina, a place called Mount Holly. This is another commercial installation. But you can see out here that as they were pulling the cables in, somebody must have felt a little bit of pressure on the other side, say, hey, it's not moving. Can you pull tight harder? And as they did that, they stripped out the insulation. Okay, caused arcing. And like I said, these problems are self-correcting. But many times during installation or inspection afterwards, you don't notice every single piece of wiring. Okay. But the fire service people have to respond to this. So what do they have to do? What are the challenges they face? So as these incidents are coming to light, we decided that we'll investigate this problem in greater detail. The biggest issue that we were worried about, especially from the fire service feedback, was the issue of electrical shock hazard. It's not fire hazard, it's electrical shock hazard, because you're going to put water on something that is energized. Or you're going to have wet gloves, wet shoes, you're going to climb on top of these things, and you are going to be somehow grounded and get electrical shock. And there are several questions about what do we do when it comes to this. There is, now that roof is being covered by photovoltaic panels, there's less space available for them to maneuver themselves. When we adopt new technologies, we don't consider those side effects of our installations. We want to cover as much of the roof as possible because we generate more power. But what will the fire service do if they have to go on the roof? There is a space for them to walk around. And then when they come there, how do they disconnect this system? What is the power that used to disconnect, and where is it located? They had no idea that there could be switches like that. And if they're cutting to the panels like they're doing here, are they cutting through conductors? Are they cutting through live paths? And so forth. So these are the many issues that we addressed in our research work. And so we looked at how firefighters would approach the panels. We looked at out here whether there's a possibility of a shock hazard when you have a hose stream directed towards energized parts of the photovoltaic panel. Okay. Nice thing we found is that as long as you have a fog rather than a stream, you're in good shape, because then the electrical conduction back to the firefighter is nothing. We use salt water also, because it's possible in some places they have salty water. So we try to figure out many ways out by which we can give firemen guidance. One of the things they felt they could use was firefighting foam to blanket the panels so that they can reduce power generation. What we found is that because photovoltaics are slightly warm, a couple of things happen. One is that the foam starts to dissipate pretty quickly. Okay, it doesn't stay in place. Secondly, the blocking power of foam is not very great. It's good refractive material, but doesn't really block sunlight very well. So still, enough sunlight gets through it, even in your layer of foam on top of it, for it to be generating power enough to give you electrical shock. We also looked at how many ways of covering a panel. So if somebody were to visit your home, you had a fire event, and they wanted to cut off the power, could they use tarps to cover it? I mean, we found that if you use plastic tarps, they're useless because they still transmit a lot of light. And so you use thick canvas type of tarps, you want to be really effective. And what happens in the night if you have a fire in the night? Well, the lights from the fire service people could start to energize this panel in the night. Okay, so you can see that there are hazards associated with this installation that we had not investigated before this became a mainstream adoption in the US. We looked at various different technologies: panels, laminates, and shingles. There are three major technologies that are currently being used. And most of the tests was done in realistic structures like this. Again, fire service people involved to come and watch and participate in this testing so they could understand what they were saying. We also looked at how many ways you can actually create a fire from an attic space that might involve a photovoltaic panel. It's not very easy, but it does happen. It can happen. All this is available in our research report on our website. And then I'd like to talk a little bit about ventilation. Bob James is going to do most of the tactical discussion. So if you're really interested in tactical discussion on ventilation, you must go and listen to his presentation. All our work is done on realistic structures, as you saw before. It's either a one-story, 1,200 square foot, or 3,200 square foot, two-story building. Typical US homes. This particular home has got a high atrium space, a 17-foot high ceiling in the front. The great room that I showed you, we built a great room out here. Okay, and one of the big reasons for doing studies in this kind of structures because it's more credible for the fire service to believe us. When they get the results, they feel it's more related to their environment. Second important reason for doing this in structure is that when you do field experiments, these structures are very similar to what's actually existing. So we can develop better correlation between the lab and the field. Let me go back. And the third thing is I mentioned earlier was using realistic fuels. Okay, if you're using a kitchen, you must have a kitchen type of cabinets, wooden cabinets and stuff like that. Bedroom should have mattresses. Living room should have couches, carpeting, etc. So as realistic as we can possibly, including toys. We sometimes put toys so that it looks very similar. And that's to make the whole story credible and the data really acceptable to our audience. This is interesting. I'll rerun this again, but I would like you to watch this video. Okay. This is a video on ventilation and the power of ventilation. So as you know, it's an attic fire. We put in a small crib in the attic, ignited it, and we wanted to see what kind of fire we could get. The whole attic space as well downstairs is closed, so only available air is what is in the attic space. That's some of those members, I think, cracking inside the attic space. So when you think of this as flashover, right? Okay, so put itself out. When it ran out of oxygen, it put itself out. Okay, it seemed like a severe fire. One thing I did not tell you about this particular test is that there is no opening on the roof. We had cut a 4-foot by 4-foot opening for doing other experiments, but for this experiment, we put a piece of plywood over it. Okay, that's why you see the smoke coming out from the ends, shooting out from that angle. It's not coming vertically out as you expect. It was a complete opening. So the only air available in this test was in the attic space. There's no more, and I guess other air that may have leaked inside as it was trying to muscle through the roof system. But you can see the power of this fire. But yet, you remove the oxygen away from it, it is self-extinguished. So this is very interesting for us to study how ventilation affects fire dynamics. The importance of controlling the ventilation, I think the key point here, is that when a fire service personnel is entering the front door, he's actually creating a ventilation path. That activity itself creates a ventilation path. So what's the consequence of a ventilation path? It's going to add air to it, therefore it's going to restart the ignition process, add air into the combustible fuel. Temperatures are going to increase, as we saw earlier. And something else has to go with it. And again, what we found is that you have to coordinate that opening of the door or controlling the door space by starting your suppression line at the same time. If you did not do that, then all you're doing is feeding air into the fire, therefore making the fire go bigger. Okay, these are very, fast individuals working on a lab building a 2-story structure. I'll just let it run for a couple of minutes, because then you can see how these structures are being built. Again, this is a time-lapse movie. The whole building took about 2 weeks to build in the lab. Also, just want to point out that this is a single-story structure that we use, and that's a 2-story structure. The whole 1- and 2-story structure fits inside our large fire test lab that we have. Okay, it's like a 40-meter by 40-meter square area, so pretty large, about 16-foot ceiling space, so very large ceiling space available. Allows us to do very nice work in this area in a very controlled environment. The beauty of these experiments are that we can control the variables. Now, when the fire service go in the field, their experience is based on one of experiences. So in other words, they might see something, they think it's important, but they don't quite realize there are other variables connected with it. What we try to do out here is to reduce the number of variables in our testing so we can really understand the consequence of various important firefighter tactical moves that they make during a fire event. The building itself, while it's made of wood structure, you see the outside skin out here, that's non-combustible material. It's more like a cementitious board. So that we can do multiple tests. Now, each of these structures, probably we can do about 20, 30 tests. Inside the building, we lined it with gypsum wallboard, 2 layers of it. One of them is sacrificial, so if it gets damaged during a fire test, we can very readily replace it so that we can do a retest very quickly. And we can do we can do 1 test a day in this structure and 1 in this structure. The reason for only about a test a day is because of instrumentation, because in the fire test, the instrumentation does get damaged or they get displaced because of fire service activity, and therefore we have to relocate the instrumentation. That takes about a day for us to do. Inside the structures, this gives you a 3D view of what the structures look like. Out here, in this particular case, there is a tall atrium space in the front. This is a very typical, I would say, relatively small ranch house in the U.S. Very similar, very typical structure of the ranch house. And the various, how it's furnished in the bedrooms, living room, typical furniture you would find, kitchen. We also get some appliances, cheap appliances to put in there. Because many times they have insulation, that can burn also. So it's as part of the system. Fair amount of instrumentation goes into it. When you're measuring temperature, each room is instrumented with thermocouples vertically, as well as in key strategic locations. We measure gas concentrations in the key rooms where fire events are going to take place, or in adjoining spaces. In most cases, we will have oxygen, CO, and CO2 analyzers, which are very easy to deploy. They are standard 1-gas analyzer. But when we do something more sophisticated, we can have extractive FTIR included into it. And then, obviously, all our tests are video imaged. We have 8 views shown out there that we can show at one time and put it together. So you can look at the fire from various angles at the same time. Here's a one-sided experiment that we conducted. I'll show you some data. Where we started ignition of a sofa and a bed. What we'll do is typically when you do this experiments, at some time we're going to ventilate. So the fire starts, we close it up, we let it go under-ventilated, and at some point we're going to ventilate. And then we'll allow fire service people to say, okay, what are you going to do now? Here's your protocol. You got to wait for 2 minutes before you open the doorway, but you want to control the doorway so that you can apply the hose trim, or open the doorway and open it 1 or 2 ventilations to see where the fire progresses. And then we collect data throughout the building structure. So here's what the data looks like. Again, it's very interesting. As I was listening to Bjorn Carlson's presentation, he's showing these graphs. This is the graphs, they're actual data. This is the data. So in this particular case, we're monitoring temperature 7 feet above the floor in this room of fire origin. And you see the temperature go up to about 1,000 degrees Fahrenheit, about 600 degrees Celsius. It becomes ventilation controlled. Temperature goes down. You open the front door at this point, and then you open a front window. So you have 2 ventilation paths now. And the fire quickly grows into flash row conditions. And then the fuel dies down and the fire dies down. At a 3-foot level, very similar situation. 3-foot level is important because that's where the firemen would be. Crouched down with a hose line, trying to do is search and rescue as well as try to put a fire out. It's a very similar profile, except the temperatures are lower as you expect them to be lower, right? So the temperature, again, because ventilation control, the temperature goes down. You open the windows, develop ventilation, and you get back to flashover conditions. And this kind of data is repeatable from test to test. So what we have really proven is that even though you may change the scenario and the timing, you may have door open a little later or later after it's become ventilation control, you'll get the same effect afterwards. And it depends upon how you affect your ventilation, which doors and which windows do you open. And that is reflected in the time, by the time you get that flashover condition occur.
Why do you're talking about flashover, and you can see that it is a flashover. What were you afraid that should be a backdraft?
This is flashover, yes. This is not backdraft.
Were you afraid that there could also be a backdraft at that moment? Or can you influence it in the test?
We can probably create backdraft, but no, in this case, we did not expect backdraft in our experiment.
But why did you not expect that?
Because the type of fuels we are using, we really know them very well. And we have done this experiment so many times. And so that experience tells us that we should not expect backdraft in this experiment. It's a good question. I mean, I think for practical, for developing our safety procedures, it's a very good question that you asked.
What would you change to create a backdraft in this scenario?
We could. We have not. Because I think that
what would you change to create a backdraft? What
would you change? I think we might change, add more fuel, so you get more combustible gases in the upper hot gas layer. That could be one way of creating a backdraft. You probably need a slightly larger space. Some of the rooms are small, so we might do this experiment in a larger space so that you get that mixing that Bjorn was talking about, and that would create a backdraft. Okay. Yeah, it is very tricky, by the way, to create backdraft unless you have an experiment designed for backdraft. Okay. Okay. We talk about oxygen concentrations. As I mentioned before, you might typically find when you have ventilation deprived conditions and the combustion stops around here about 5 minutes, for example. You see about 5 minutes, your concentration about 15%. It's typically at that point, you're not able to sustain combustion. And so basically it's smoldering. It's still there a lot of heat involved. So I think it's still degrading and decomposing, but it's not flaming, it's not combusting. So all the hot gases unburned gases are going up in the hot gas layer and accumulating. And once you open the window and affect ventilation, the oxygen concentration goes up, and then you have flashover conditions. And this is a similar story for CO and CO2, but unfortunately, when you have ventilation controlled conditions, you have CO units up to the limit, so you can't measure anything more. And this is 1% is pretty high amount of CO. It's 10,000 parts per million, which is typically what you expect close to those conditions. One of the things that we've done as part of the exercise to understand the tenability inside the structure at various times, and we use ISO 13571 model for heat and for carbon monoxide to understand how close to tenability fire service people may be when they're doing their various rescue services. So we look at different areas in the room at different times after we are doing this experiment to understand what the fractionally effective dose for heat and CO would be. We learned quite a bit from these experiments. I would say that one of the biggest takeaways for us has been to really create repeatable experiments. I think if you do one experiment, nobody's convinced by it. So in this series of experiments, we always try to repeat 1 or 2 or 3 experiments just to show that this is a repeatable phenomena. And when you show that, that's when you see that the fire service people get buy-in into the results you're obtaining, and they're willing to express the results to their own fire service people for training purposes. So I'm going to show you a small video of feedback that we received from the fire service.
The modern fire today, UL is looking at the fire service and saying, how can you do your job better, safer, faster, more efficient for it. The burns and the technology that's coming out here and the information is being used at the NFPA. That's going to write the codes for the future. They're looking at the way that building codes are developed, the way building codes are put together. So everybody, for us, we're kind of selfish at the fire service that we're looking at this saying, how can we be better at the fire side of this? But you can see the group of folks that are here. It's a diverse group that's looking at public safety. And if you think about that, that's really, this is about Mrs. Smith and her family. And if there's a fire in their home, what things can we do to make it survivable for them? How do we prevent a fire? How do we make a fire grow slower so that they have more time to respond to it?
Fires have changed dramatically, and unfortunately the fire service is steeped in tradition and tactics that were born out of the 70s that have served us extremely well as far as ventilation, the effects of ventilation, how we ventilate, when we ventilate. They are still being carried out on the fire ground today. Unfortunately, the environment has changed around us, and at times our tactics don't assist us in the ways we think they're going to.
The challenge is it's still working, right? If the environment changes, if the rules of the game change, if the built environment has changed so much and we continue to do things the way we always did it, then we'll get ourselves in trouble. The name of the game is to figure out when that old stuff still applies and when it doesn't, and you need data to be able to make that decision.
Well, the fire service is notorious for traditions, and a lot of our information is passed down through textbooks and just through generational person-to-person transfer. One of the things that we're doing with these tests are proving or disproving that some of those tactics were correct. Like for years we've taught that a 4x4 ventilation hole is the perfect size. Well, now we're trying to put the science to that to determine maybe it is. Maybe the information was correct all along, or maybe it's only applicable in certain situations and we need bigger holes for newer fire loads or what have you. So it's proving that some of the things we're doing is correct, and it's also giving us new information to expand our tactics.
You all is providing us with the information we need to do our job in a modern fire environment. I couldn't tell the lessons, I couldn't convey the lessons I'm conveying today in the classroom without this information. My experience didn't teach me what I'm learning here today. This is the only place I can learn this. I can't go to enough fires to learn this. I just can't. And so if I don't come here, if we don't have access to this kind of information, and we don't have it packaged the way it's packaged, then we can't learn our job.
My ability to make command decisions on the fire ground has been increased tremendously by the exposure I've had through this testing. My decisions are more concise, more directed, crisper. I can react and implement strategy based on the knowledge that I've received in this controlled environment where I'm not going to endanger members' lives. I'm learning here in this controlled environment things that might take me years on the fire ground to learn and understand.
But research is only, it's great knowledge, but the fire service benefits when we can get that knowledge out to the fire service. And I think an important role that UL has done is creating the educational pieces on the UL website so our fire companies can go and watch it at their own pace, start to learn what their work environment is and how it's going to perform. And then also they've done an important role of getting their members out to the fire service and at different functions to deliver that message and deliver the data that they're collecting. Because we're seeing that our tactics are going to have to change, that we're going to have to make informed decisions, and that information has to come from data that's research driven. And I think that's going to make our members, give them the ability to make good decisions on the fire ground.
Okay, the reason I wanted to show this video is only one reason, is that, it's a discussion about how we are translating what we're doing back to the fire service. And the people that you saw in the video are really the people who are doing it. And there are, we are getting a growing army of fire service people who are volunteering to take the studies that we've conducted and go and talk to their own people about how they want to make changes. Because we as people from UL cannot make those changes. That has to come from the fire service themselves. And we realized that for us, it was very important to develop very credible base of data. Once the data is developed, we have to really get partnership from the fire service to get it translated into practice. They can adopt the knowledge that we generated to make sure that it suits their situation and their practices. And they can then watch their practices and see if they're getting improvements in reduction of injuries and fatalities. So that's the story. Thank you very much. I'll obviously take any questions you might have.